So we're going to talk about the deposit, Kennedy deposit, which is just very close to Mount Garnet in North Queensland. I'm talking about this, but Brendan Bradley is the technical director for DevEx Resources, and if it wasn't for him really saying go out and look for these things, this deposit would never have been found. It's a purely conceptual discovery that kind of is only about 2.5 years from discovery to a resource. There's a disclaimer from DevEx here, and what I will say here is that some of the slides will have the reference to DevEx's ASX releases down on the left-hand side, and there are some other references and acknowledgements which I'll do at the end. So that's a disclaimer for those folks. It's a very simple diagram. Mount Garnet up in the about 2.5 hours west of Cairns, and this deposit is literally right beside Mount Garnet. I'm going to talk about not so much about the discovery, because we've sort of talked about that before at a conference in Charters Towers, but I'll talk a little bit about that. But what the concept was when we went looking for this style of deposit, I want to talk about the geology. The resource will get a brief mention, and we'll look at some chemistry with respect to the metallurgy. You don't go looking for rare earth deposits just for the grade. You've got to get the rare earth elements out of the rock effectively and cheaply. So we're going to look at this. Now, this is just a model for what we were kind of looking for. We wanted a clay, an ionic clay hosted mineral resource. And what we have is this is a kind of the, if you like, the South China model. We have some sort of, I'm pointing here at granitoids and an upland features. There's some downslope erosion and or just lateritization on top of a granite or a rock that is enriched in rare earth elements. And the ionic clay type deposits sit right on top of here. So you essentially weather the rare earth elements into something else that is not a primary mineral. One of the key things about this thing is nice tropical, subtropical conditions, lots of rain, lots of nice warm weather. So it's kind of a statement, you know, I might belabor this, but, you know, this ionic thing is really about a chemical weathering of a rare earth bearing rock of some sort and subsequent weak adsorption of that rock on the secondary minerals, and often they are clays, kaolinite, halloysite. This is essentially, and I've got a little, so my little diagram here is a mica, and it's got these little these rare earth elements on it, and it's literally essentially an electrostatic blonde. And the extraction of those rare earths, if you want to get them off those clays, you need a bit of salt water, a little bit more than that, probably ammonium sulfate, magnesium sulfate. You need a pH that's sort of about 4 or 3, ideally, and you just do it under ambient conditions, and you can leach it. So you can take those rare earth elements off the micas or off the clays and take them into solution. That's the ideal. That's the kind of ideal. That's the sort of thing we're really looking for. And what does that lead to? It leads to lower capital costs for a deposit, you know, setting up a deposit, you know, it's kind of a leach type arrangement, and lower operating costs. And I'm talking about lower than a hard rock deposit, where you're taking something out of a carbonatite and you have to take all those minerals apart and get the elements out of those individually. And consequently, it enables lower grade deposits. That's the basic concept behind this. So what I'm saying here, the clay deposits, generally these sort of large, low-grade things are aerially extensive. They're often near surface and they're lateritic. low capex, low operating costs. And I do that. I sort of put simple, metallurgically simple in inverted commas because they're not all metallurgically simple at all. The South Chinese model, low relief, tropical weathering. Rhyolites formed on top of, rare earth enriched granites, and there's a concept of cerium immobility and heavy rare earth concentrations that we'll kind of talk about a bit. And here's some variations on this thing. Makuutu is a project that looks very much like the Kennedy project, and this is what we use this. So it's a laterite developed in the sedimentary basin, which is overlying and adjacent to granite. So the granites erode into a basin, and the laterites are formed on it. Stanmore, which Ken talked about a few weeks ago, is a laterite over an alkalic intrusive complex where you have these alkalic rocks that are inherently enriched in rare earth elements. The Cerro Verde one is same sort of thing, but it's over a periluminous A-type granite. They can be over A-type granites, they can be over I-type granites, they can be over S-type granites. This one here, the really rich one, is quite good grade in Brazil, over a nephelinite cyanite, and our friends down in Tasmania have it sitting, the laterite forming over dolerite and alkali basalts. So there's a whole variety of these things. Now this is kind of these papers outline these profiles. Here's a lateritic profile that's sort of about 12 meters deep. Up here in the top of the profile, look, we have some sort of minerals here that are rare earth enriched. Sorry, a rock that's rare earth enriched, and we like minerals that are not resistive too much. Monazites are quite resistive, whereas some of these other ones, fluorocarbonates, you can get essentially they weather more easily. Up here in the top part of the zone, and this is the sort of the Chinese model, is because cerium has this 4+ and 3+ oxidation state, cerium will actually get fixed up here where there are lots of iron and manganese pisolite as cerium. Right. So we have in these chondrite normalized diagrams, we have a positive cerium anomaly. So this is a chondrite normalized diagram that has light rare earths on this side, heavy rare earths on this side, and there's this little spike here that is a cerium anomaly. It represents a cerium anomaly that's greater than 1. If you go down here, the rest of the rare earth elements, cerium sticks up on the top here, mostly. The rest of the rare earth, including the heavies, which everybody's interested in, well, there's 2 lights and 2 heavies everyone's interested in, they move down in the profile, and cerium gets stuck up there, so you get a negative cerium anomaly here. This is where the goodies are, the rare earths are, and this is the sort of the ionic absorption zone where these elements link up with kaolinite, halloysite, some illite, and the cerium sticks to the surface and it's depleted down here. Down in this rock, there's no cerium anomaly, negative or otherwise. That's kind of a nice little model. And the reason things, the elements we're looking for drop out here is because you get a gradual increase as you buffer going down in the pH. That's kind of part of that model. Now, the discovery of this was really based on a systems model. We went looking for a whole lot of things: alkali rocks, A-type granites, peralkaline rocks, evolved granitoids, I would say. And we looked at, how do I go back? Oh, here we are. Sorry, I'm back. We looked at old reports, and I'll show one slide about the work that we looked at there. we looked at a whole lot of whole rock work, and if you go to exploration databases, the government exploration databases 4 or 5 years ago, there was no rare earth data. You had to go to government studies, university studies, some databases that GA was putting together, and in fact, the Geological Survey of Queensland provided some unpublished material as well. And there was an excellent stream sediment survey, you may recall, of the Cape York Peninsula. So that was a thing we used here. What did we find? We found an area, and I'm going to put a diagram here, folks. But the people who are listening out there won't be able to see. But to the right-hand side of the big red ellipse is about where Mount Garnet is. And Mount Garnet is in a tin province, which is the Herberton sort of tin province. It is characterized by a bunch of Permian-Carboniferous, or mostly Permian and Carboniferous granitoids of various types. There's lots of grisons. The little black lines down here are the tin dredge tailings throughout the district. And they intrude the blue and the grey and the light blue rocks there, which are the Chiligo Formation, the Hodgkin Formation, which are the, I guess, Devonian, Silurian equivalents. In fact, Mount Garnet, of course, is a skarn where those intrusions have gone to the Chiligo Formation and formed a skarn. But the interesting thing about this area is that to the south, now I'm looking at the brown areas here, is a little sedimentary basin, or it's a shallow, restricted sedimentary basin that the Geological Survey map has been tertiary in age. And it is intercalated with the other darker brown here, which are the basalts, of the McBride province and the Atherton province. And they're intercalated, they're interbedded. And the geochemical data that we found suggested we have elevated, and I'm just saying anomalous sample here, elevated rocks in terms of rare earth elements, especially heavies. And to the south, in that just stream sediment survey, there were also elevated anomalous samples with respect to heavy rare earths. That's what led us into the area in the first place. So we got these were the first two tenements that we picked up, that red one to the north. The interesting thing was the existing drainage patterns are from north to south. The Herbert River comes down through here somewhere, and it's a tin-rich, cassiterite-rich deposits there. So we were thinking, well, there are elevated rare earths, there's fluorine, there's all sorts of interesting things, evolved granite. Let's go and look at this. The only other thing here, is there a black line across here? That's where people generally place the Palmerville fault. And I'm suggesting perhaps the Palmerville was actually active during the tertiary, and these are there may be little pull-apart basins associated with this volcanism. This is widespread, shield-type volcanism. So there's these little sedimentary basins in here. Just to look, so that tenement I pointed out was the sort of central tenement here. These are the drill holes, the white dots are the drill holes, and you can see underneath there is a major magnetic anomaly, and in fact that's the Hammond Creek granodiorite, right, that runs underneath the basin. But what's interesting is that most of the resource kind of sits on this lobe of the sediments that comes down through the basin. So whilst the Hammond Creek granodiorite comes down through there, there are also a bunch of granitoids that are showing up all over the place and that are magnetic in the area. So black blodges are the dredge workings and tailings, and you can see the existing drainage pattern through those sediments goes from the northwest to the southeast. So there's a lobe here. Now that lobe, where you see most of the drilling where I've said inferred resource, inferred resource is the orangey patch there, is over 10 kilometres long. It's probably more like 12 kilometres long. It covers 50 square kilometres. This is a topographic map that shows it's a very flat area. There's a slope down to the south or to the southeast on both, and there are slope and both. There's various lobes of this material all over the place. So there's a resource sitting out there. Now that resource is there. It's an inferred resource because anywhere else we drill, we don't have enough. Whilst we have interesting results and good results, we don't have enough to put together a resource. This is what it looks like. So it's flat as a tack. It's got scrubby, eucalypt, cypress pines, a lot of lantana, typical sort of grassy areas of North Queensland, and this chocolatey brown clay that sits on the surface. Now, if we went back, one of the other reasons we got into here is we went back to a report that has dug here today, probably Doug Young wrote. And now this is the northern part of that tenement. This is Mount Garnet. Those are black lines of the dredge workings. And there was actually an old lease here because it was put over a magnetic anomaly, which is in the basement underneath the sediments. But there are a bunch of holes drilled here looking for tin within the sediments and also pushing holes right through into the basement to look at what was going on in the basement. The interesting thing about this is when we looked at this data, they described clays and lateritic. Lots of clay, lots of laterite, and that was a major factor of us going to look there. And that's down to 30 odd meters. Okay, so what also another old cross section from Doug's report, and I've taken the liberty of making this red thing underneath. That's the granite. The vertical exaggeration is probably 20 times here. I can't remember what it is, but it's a biotite magnetite granodiorite that sits underneath the basin. That's about 90 to 100 meters deep. There's a cycle of sedimentation which is very conglomeratic, lots of nice clean quartz wash. There's probably about 3 fining cycles here. Then you get this basalt comes in and interrupts everything. It's about 20 meters of basalt. It presumably went down all the river valleys and kind of stopped things. And above that, you get very restricted flow. It must have been a lacustrine environment. There's some conglomerates, some sediments, but basically it's a clay siltstone, clay mudstone sort of mix, and it's largely unconsolidated. Our drilling would have only gone down to about the top of the words that say poorly consolidated sediments. So our drilling was very shallow. So we're only looking in these clay rocks in the top of the basin, in the upper part of the basin. In the early stages of this, we just drilled 11 holes. 11 shallow holes to 15 meters. And these are kind of the results. And of those 11 holes, probably I think 8 or 9 of them came back with this really interesting top 2 meters, ran well over 1,000 ppm trio. So I'm expressing total rare earth elements as oxides, and I'm including yttrium here. And not only that, we also got a layer down here a little bit deeper that it was also anomalous. And these are very wide space holes, 1 to 2 kilometre wide space holes. The company took the data, rather than rushing off and trying to get a resource, they took the data, they ran the samples through ANSTO, looked at desorption results, and got very good metallurgical recoveries in a very short period of time using ammonium sulfate leach. So I'm not going to talk about that early stage, but I'm going to talk about more detail about the subsequent ANSTO program. Now I'm not going to show you this. I could draw a section any which way across that lobe, but this is the sort of thing. We got a top layer that's 2 meters deep, a little bit more in places, a little bit less. That's kind of 150 to maybe 300 ppm magnet rare earth oxides. So these are the interesting elements we're interested in, these 2 heavies and these 2 lights. And we've added them all together, and those are the numbers we get. And we call that a piezolytic clay. And down here, we also get another piezolytic horizon that is one lower down. We also get another piezolytic horizon that has lower grades, more discontinuous, but it's thicker. That's the basalt I showed you in the last diagram. But I don't have the holes here. Right above that granite there, right up on the left-hand side of the screen, we drilled into the granite, and at the saprolytic contact at the unconformity, we got 7 or 8 meters of twice that grade, twice those sort of grades sitting in here. But we didn't get much of it. But that was pretty interesting. We didn't get much of it, so it's better grade than those piezolytic things. So that's a sort of a separate environment. Now, just to go to the resource. So I'm going to go back. There's that lobe, and the resource is in that sort of little dashed line through here, and the thematic here shows you the trio: total rare earth oxides less the cerium. We're not, because people try to get rid of the cerium to show what other elements are worth. Cerium's not worth much, so they try to show you value in what's something less cerium. And these are the resources down here. This particular outline is the 325 cutoff. And you see that if you get rid of the cerium, so that's 1,000 ppm trio. If you get rid of the cerium, you're getting rid of half of your rare earth grade. So cerium is quite a major component. So people like to produce, so there's 500, say 500 ppm is half of that. It's the same for the other cutoff, really. These numbers here, the magnet rare earth, this is the resource magnet rare earth, which is 100 to 180 and 220, are comparable to other deposits that are published elsewhere. Now, I can't show you, because of the nature of this talk and the ASX, I can't show you a comparison, but I would refer you to Ken's paper on just this topic that allows you to plug those numbers in and compare it with other deposits and the value of other deposits. I can't show you that because of the nature of what happens with ASX. But here, this deposit sits, the surface deposit sits on the surface. It's free digging, if you like. There's no drill and blast, there's no waste. The infrastructure is right there, and it has a real amazing scale with amazing metallurgy, which we'll deal with in a minute. So if people want to take those figures, they can plug them into Ken's paper, and you'll see a comparison. Let's go back a bit. There is a section across here, section A, and it's a resource section. This is published data. The resource that is published is this strip along the surface, but you can see there's grade down here, and that was the sort of the lower zone. That's the top one's the upper zone, the well one's the lower zone. Now excuse me. So this is a probability plot based on lithology. So we logged these things, we allocated grade to each interval, and we said what's the probability. So what you get is a bunch of gravel. There's some gravels, there's sands, there's sandy silts, and there's clay, basalt, weathered granite. It's a saprolytic granite, and this thing we call the piezolyte clay. What's clear from this is that the coarse sediments, the propensity for mineralization, and this is trio less cerium along the bottom, the propensity for mineralization in the coarse sediments is kind of low. When you go to the clay and the silty clays, it's better. This is the yellow. I'm talking about the yellow here. When you go to the piezolytic clays, there's a significant kick up in the amount of samples above any given cutoff. We use 375 or 325, which is down here. There's a lot of samples there, but also there's granite has significant numbers that go right up here. And the basalts, which are a little bit alkalic, can get up to 0.3% total rare earth elements. If you look at chondrite normalized plots of these, looking at the lithology only, you can see that those sediments, including the clay, just clay without pisolites, they have all much the same shape, and in fact they have the same shape generally as the granite, not quite the same. So our inference here is that in fact the granite is actually supplying a lot of that sediment into the basin. The basalt, on the other hand, is quite different. It has quite a different shape at all. It's probably not the source of the rare earth elements. And the piezolitic rocks, the piezolitic clay, which we'll look at shortly, also looks like a lot like the granite, but it has this very strong, very, very strong cerium anomaly. And we'll look at that a little bit further. So here's what some of the surface looks like. We don't see the whole profile here because this is a bulldozer cut here. But not only are those things that they're piezolites plus nodules, and there's a lot of very fine clay in amongst that. And I'm going to show you some drill samples now. And what I've done is picked out the samples that are over 100 ppm magnet rare earths. So 4 important rare earths that everybody's looking for. And these are just a bunch of holes that I picked out initially. And you see that below about 2 meters, so this is 0, the half meter samples down to 4 meters. And then there's 1 meter sampling. So in that top 2 meters is where we see the elevated rare earth grade. And under that, the grade drops off quite markedly. In fact, and you can see also it's a very dark layer up there. That is a zone of strong piezolites with iron and magnesium oxides. As you go deeper in the hole, there's a lot of goethite, and there's a lot, and even hematite down here. But you can see there's quite a marked change in those. Same sort of diagram here. The next one, I've done the same. I've put 100 ppm. Now, the bottom of each of those plates is 0 to 2.5. Those 5 bottom samples goes down to 2.5. So we've got in the very top sample, we tend not to go over 100 ppm, but it's not too far off. And there you have this is what makes up the resource. And there's that dark sort of chocolatey brown color. That's let me, for people who are looking on Zoom, in KAC005 down on the right hand corner, 2 to 2.5 grams. It's quite an elevated number, and it doesn't look very dark, but in fact that's a large nodule of manganese oxide sitting there. So sometimes you get just a few of these things, manganese oxides and iron oxide nodules or piezolites, it's broken there. So that grade is quite good. So that when you see a lot of these manganese oxides and a lot of these piezolites and iron nodules, that's where the grade is. Now we were fortunate enough to do some bulk density work, which you have got to do if you want to do resources. So we use these push tube things. You push a tube down and you pull the sample out, and so you can see what we're actually looking at here. And in that 2 meter zones, it's not just a simple 2 meter zone. There are at least 4 lithotypes. There is a silty clay on the surface. There is a piezolitic clay with iron oxide, very sparse iron oxide. There's a crowded piezolite with strong manganese and iron oxides. And then, which is down here, that's that very dark material. And then you go into saprolitic material that's highly variable. This is the top part here is very fluffy, porous texture. This one here has got piezolites, but lots of clays, but not many piezolites. And here there's a lot of clay, but here can be you can actually be lithified down in the so even if we're only talking 2 meters here, there's quite a lot of variability in that 2 meters. This is busy, and I'm not. This is that the 4 lithotypes here, and what I'm going to do, and I saw the advertisement for ALS there on the. So we used who's the ALS person here? We talked about this before. So what we really liked about the ALS techniques is we could use a lithium borate fusion technique, which is for magnet rare earths, and it's just elemental here. It's not oxide. This, and we did analysis down this. It's a 1.7 meters sample here, and then we did the ammonium sulfate leach, which is MEMS 19, but we asked for pH 4, which is 19A. So in theory, if you have those 2 analyses for the same thing, you can get a recovery, because this thing here, this particular technique focuses on your clays. Now, what ammonium sulfate leach, what rare earths can we get off our clays, and they give us a P number in ppm. It's not a diagnostic leach. It's just an extremely good exploration tool. So we have what I'm bringing you. There's a busy slide, but this red area here is where those packed piezolites, which are manganese rich and iron rich, are, and they have the best fusion results for they're plus 300 ppm for magnet rare earths, but they have the lowest recovery. If they have they have best results, but they tend to have the lowest recovery. In fact, the best recovery from material is actually in this zone up here. We have fewer piezolites, but lots and lots of clay, and so the notional recovery is a lot better. Up here in the top here, the silty clay up here is almost entirely silica and aluminium. So these, the lateritization process has gone on quite well here. There's a strong area of intense piezolite formation, and then you go into the saprolite. Incidentally, we also did some XRF analyses down here, and the elevated rare earths correlate with these other elements: lead, cobalt, chromium. We correlate with these things as well. They're not high, but there's a definite correlation. One assumes it's because the manganese oxides and the iron oxides are grabbing everything around. So we're not just interested in the grade, we're interested in the recoveries. And this is a sort of a look-see before we did work with ANSTO to looking at these things. So here's the same diagram, and this is the idea of the notional recovery as one analysis divided by the other times 100 gets you a recovery. It's a good exploration tool. You see the saprolite at the bottom, and the piezolites and the silty rocks don't have a positive cerium anomaly. The cerium anomaly is with the intense piezolites. The better grade, which is down the bottom here, the better grade is with those intense piezolites, but it's got low notional recovery. So there's an area down here that has best recoveries and a moderate grade. What does all that say? What happens here is when you're taking a sample to do metallurgical test work. We just took the 2 meter sample. What we're saying is within that small area, those 4 lithotypes, the recoveries and the grades are quite different depending on what you sample. But when we did the work for ANSTO, we combined all that stuff together. We combined all that stuff together so that the actual results depends on how many piezolites you've got in it, how much clay you've got in it, and so it's quite. You've got to have you've got to take the one sample through the 2 meters to determine that. Even though on a detailed scale the results are quite different. So what do we do with ANSTO? We got funded by the 8th round of the CEI. We took samples from that top resource zone, the 2 meter zone. We took samples from the bottom zone, and there was some granitoid stuff here as well. This shows you now. This is a diagram showing the magnet rare earth recoveries, those 4 elements, at a pH 4 over half an hour. So this is very quick. What is the recovery that happens when you dissolve it? When you put ammonium sulfate in there, pH 4 for 30 minutes, and it's only 22. We like this diagram because the upper zone, which is the resource zone in magenta, is mostly above 40%. It goes up to 70% places. Yet the granite-related rare earths and the lower related rare earths don't not of interest because the recoveries are just too low. The mineralogy of this suggests it's almost all clay and silica. There are some amorphous silica and iron oxides. There's a lot of the goethite and things up here, but mostly this is quartz and silica up in here. This, however, actually has these lower zones actually have original granite silicates. There's hornblends and there's feldspars and things. So the recoveries we don't look at this material, we look at this material. Those numbers are quite good, and like I say, the samples we took were composite. These, even though we've got 4 distinctive lithotypes, we've composited them all into one. This is from the ASX release that DevEx have put out. So I showed you the diagram pH 4 and for half an hour. So pH 4, someone tells me, is the pH of red wine, and I think pH 3 point something is the pH of white wine. So let's think of it soaking it in white wine and red wine for a moment. And these are average recoveries from the whole of the survey, and they're about average here about 46%, but up to 63%. If you lower the pH and soak that stuff for another half hour, you can actually get quite a jump in the recoveries of the magnet rare earths from 46 to 53. If you keep the pH at 3 and just let it soak for 2.5 hours, 5 hours, you don't actually get very much out of it. And this is what this shows you. pH 4 is the pH 4 and half an hour is blue. So most of the recovery into solution of these magnet rare earths happens in half an hour. If you drop pH for another half hour, you get another 5 or 6%, 5 or 10 to 10%. But if you leave it sitting around for a while, you don't get very much. And this is average recovery. Now, this over here, these are the samples that were taken within the resource, and the thematic on these actually gives, it's not the average, it's the actual number, and these are quite good recoveries, plus 40% recovery, and they're consistent almost all over the resource for 50 square kilometres, as is the grade. I just talk a little bit for the folks who, there's a bit of metallurgy here. If you look at the gangue mineralogy, and this is trio, so this is total rare earth oxides plus yttrium, which is what I've been talking about, and to the iron aluminium ratio in the resource, it's plus it averages about 1.56, which is above that number 1 line there. So if you got things above 1 in that line there, that's pretty good. If it's below the line, it's not so good. If you increase the if you decrease the pH, make it more acid, and you leave it sitting around for 5 hours, then you clearly take more into solution. So what this is saying is that more iron and aluminium go into solution with lower pH and longer time. That is kind of logical, really. And so same with silica. But this is kind of what everybody's interested in. The numbers up here, so it's very early stage work, where you get 40 to 60% recovery through desorption. So you put this material in, it's got clay, it's got rare earths attached to clays, you put it in a solution, very cheap and effective way to do it. It goes off into the solution. It goes off into the solution, and you get significant recovery. And that's almost the definition of an ionic rare earth deposit. If you look at some of those papers, they say, you know, if the most of the recovery is 50% of the recovery is by this technique, then that's an ionic clay. So, but what next? Really, this is very early stages, really, really early stages. So one thing that hasn't happened is we do not know what the mineralogy is. And that's really the key to any of this stuff. There'll be no mineralogical studies yet. So we've just have got some samples, and we are cooperating with them on a study with them. You know, these are really metallurgical features. We could go and drill more holes, and we could expand that. We could drill more holes over that 200 square kilometres, and we'll increase the resource to whatever it is. You know, the grade is very consistent, the recovery is really consistent, but until you get some of this information, there's a little point. So the next step is really a whole lot of further metallurgical work, test work. You know, can you produce a mixed rare earth carbonate, which is what everyone does to determine how saleable this product is? What does it cost to produce that? You know, all those sort of things. So it's very early days. So in conclusion, excuse me. In conclusion, you know, what we have is this extensive near-surface mineralization. And it's possible, you know, 200 square, where the resources covers 50 square kilometres, 2 metres deep on a flat terrain that goes from all over the place. Could be 200 square kilometres. It's got really good ionic absorption and desorption characteristics, so you can take it into solution. It has dense laterite profiles, only 2 metres, within which there are lithotypes that have quite different responses to the recovery to metallurgical techniques, and have different grades. And you've got to build that into that idea. This probably occurs within this restricted basin and tropical weathering conditions. I say that if it's raining in Mount Garnet today, this deposit's still probably forming. And the likely rare earths are probably the granitoids. There are some indications there might be peralkaline or A-type igneous rocks, but it doesn't really matter. They're there. It's an interesting deposit, and like I say, you could take the data, plug it into Ken's paper, and you'd be able to compare it with other resources around the world, and you'd see there's a it's comparable in terms of size and grade.
Now, I'm sure there are questions.
Thanks, really interesting talk. Well done. Couple of questions, if I can. First of all, what's your recovery from the licks of it? So, what do we know about?
Well, that's
the product.
We don't.
And then the second question, which I'd like, is mind you, what do you anticipate?
Isn't that interesting? Can't answer the first question because we don't know. You know, we know it can go into solution. So the next step, as I understand it, you really need to look to see whether you can make that carbonate, and and where do the products go and lie and all that. So I can't answer that one. And God, I can't answer the second one either. It really flat lying zone. It's got some vegetation, but some of its farmers up there would just love us because they know we could come in and rehabilitate, and they'd end up with wonderful pasture. I mean, you know, I've seen the ones down in South Australia or Victoria. They did a test run, and they did a wonderful rehabilitation job the farmer must have been so proud of. So I don't know, you know, whether you do slot mine. I mean, it's 150 million tons. Would you even mine 10 million tons a year? And how, you know, so how big an area? So the answer is I don't know, but you just got to use your imagination. You know, would it be tank leach? Would it be heat leach? You know, what would it be? I don't know.
When I came here, I thought, rare earths. I've never really been into rare earths. I've never even thought about those things. And you acknowledged that when you kicked off. You said, "Oh, there's not many geos here. Are probably going to be into rare earths." But oh my gosh, that intro and the geology there worked like a treat, and I was really absorbed with that presentation. That was a fantastic presentation, and I was watching, zoomed in. As a North Queenslander, I've hung around those areas and I've run around those same hills that you were describing, and I know exactly what you're talking about. My question was actually going to be the question that Rod asked, but how would you mine that? Because I know that there's a lot of environmental considerations and stuff, but I'm not going to ask my question.
Well, I don't know the answer. That's you know, it would be easy to do, but how? I mean, you know, one of the things to do in the metallurgical things is why drill any more holes? We can just do it, put a backhoe in and do some more bulk.
Really
So,
Yeah, okay. The guys with the paper referred to it's in all geology review. If you want to, you can download it from the web. It's a
highly recommended.
It's cool. Question: what is the uranium and thorium content of your
25 ppm and 16 ppm. 25 thorium, 16 uranium.
That's a little higher than North Stanmore. 8 ppm and 15 ppm. But it reflects the fact that during the breakdown of the rare earth phase in the rhythmic profile, wanted to move through the system and basically strip uranium and chlorine. So there could be a deposit somewhere further downstream.
Well, I you know, there's no sign of monazite whatsoever for, you know, we see. I've got a question for you, Ken. You know, you talk about ionic clay, but your leach process is hydrochloric acid.
This North Stanmore deposit, it's a very interesting deposit. It's 40 to 50 million years old. It's a fossil rare earth. It developed the Eocene thermal event when West Australia was sitting close to Antarctica and tropical forests grew from pole to pole.
Was the Miocene here the same? Yeah.
So basically, we have a system that has an ionic clay component. There are also secondary rare earth phosphates developed.
Okay.
From monazite, we get rhabdophane form. From xenotime, we get churchite form. We also have, we did the original ammonium sulfate, magnesium sulfate leaches. We get about 40% recovery from ammonium sulfate. We get up to 80% recovery from magnesium sulfate, but we get 90% recovery from hydrochloric acid. And we're developing our project using hydrochloric acid, which we're going to recycle. We're currently in the process of doing a pre-feasibility study. We have significant funding from the US government and from take-up agreements with Sumitomo Corporation. And it's a very, very heavy rare earth deposit. We have some samples in our deposit that are up to 1% total rare earths with 70% heavy rare earth total rare earth ratios. So it's a very, very significant. We have a 30-year mine life defined on 8% of our target. So yeah, it's something that's
I think that's what I was implying here, is that in the future, you know, it's not just the ionic component. That's why, you know, it could well be that you go to hydrochloric acid and you get, like you say, 90%. So this is a very early stage, and you know, the thing we don't have a handle on is the mineralogy.
What you've discovered is really interesting. Just illustrates the wide variety of opportunities there are in find new mineral deposits. One of our key tools is PXRF for
That's all.
that's the key.
And well,
That's
that's what we did too. Yttrium to scan what we're going to sample and what we weren't going to sample. PXRF. Yeah, no.
I noticed on one of the early sections that you showed at the basalt there, isn't it basalt that fills that valley or lowland always underlay the deposit we've ever drilled?
You know, don't know. That's the only section. But further to the south, we've actually drilled through into basalts and very shallow areas. So we've drilled through sediments into basalts further to the south. But in that particular spot, that's the only section. It's because Doug drilled those holes way back then. We didn't drill those. None of our holes have gone beyond about 30 meters. So we don't have the whole architecture of the basin sorted out.
It's unlikely that that would be the source, but it could be important to the hydrogeology as an
I think it's important. I think it's important is that it clogged up the sedimentary system.
Yeah.
That allowed then a sort of a lacustrine place where it was just clays, little incursions of sandstones and conglomerate, but it was a very quiet system that was probably just subsiding very slowly. And there's clearly two exposure times. There's that lower lateral horizon that was not well developed, and now this other one at the top that is, which is extremely well developed on the surface, and you would suggest that it's been sitting there for a while. You know, I don't know how fast laterites form, but it's been sitting there for a while, stable, and the conditions are such that you get, it's hot up there and it's wet. Not as hot, probably not as hot and wet as it was during the Miocene, deeper in the system.
Chris, just a quick question. What drilling technique did you use? And the second question, why have you not got indicated resource?
Okay. First one is mostly air core. There is some RAB. Early stuff was RAB. Almost all exclusively air core. Look, there's probably there needs to be. So you got this flat horizon, and our topographic control is basically drill hole collars and some very I think it came from magnetic survey topographic control. If you think about 50 square kilometers, and that topographic control, it changes the resource very significantly, right? So indicator's not there yet, not by a long shot, I think. You have a bit of topography in there, and you could change tons significantly. Sorry. Absolutely. So yeah. So it's an issue. It's all I say again. It's a very early stage project.
Any other questions? Yep, Julius.
Julius Marinelli, full over. I noticed a subtle dip in the holmium. Any reason in that?
The dip in the
holmium, heavy rare earth, HO?
Don't know. I don't know the answer to that. Yeah, you mean in terms of recovery? In terms of recovery, you're talking about in terms of recovery.
Just on the right place.
Oh yeah. No, there is that. And there's also something in the yttrium does the same.
Bob? Yep.
Oh, sorry. I know you've got a bit of alluvial tin nearby. Is that anything like a guide?
It's kind of why the fact that you had these evolved granitoids that was tin tungsten rich, a lot of fluorine, topaz rich granitoids, and that basin, the area that we're exploring, was extensively tested by Tablelands Tin and Doug's company so there's lots of little shallow drill holes all through there. Interesting, no one's encountered much tin in the area that we're looking at. It all seems to be to the north more recently, and then the tailings come from the north down to the south. But the actual sediments, doesn't appear to be much tin in them at all, which is kind of odd.
Going downstream a bit.
Yeah, we're downstream a bit further than the main areas of mining. Certainly, maybe the rare earths got through there. I don't understand that. The cassiterite would drop out pretty evenly, but there's two parts to that basin. There's a very active conglomeratic quartz wash lower zone, which evidently doesn't have much in it. Then there's a basalt that stops everything. Then there's this clay above it. So I don't imagine that's active enough to actually get tin deposits being formed. I was thinking you need a relatively active environment to clean, to winnow and clean the stuff. Or if it's just a sort of a sludgy basin, which is clay and nothing much else, I don't think tin's going to get in there.
Thank you once again to Chris.
That's welcome.